Oxidation-reduction reactions. Whereas acid-base reactions can be characterized as proton transfer processes, the class of reactions called oxidation-reduction or redox reactions, the reactions are considered electron transfer reactions. Oxidation-reduction reactions are very much part of the world around us. They range from the burning of fossil fuels to the action of household bleach. Additionally, most metallic and non-metallic elements are obtained from their ores by the process of oxidation or reduction. Many element redox reactions take place in water, but not all redox reactions occur in aqueous solution. We begin our discussion with a reaction in which two elements combine to form a compound. Consider the formation of magnesium oxide from magnesium and oxygen. This one. Magnesium oxide is an ionic compound made up of magnesium plus and 2 plus and oxygen 2 minus ions. In this reaction, two magnesium atoms give up or transfer 4 electrons to 2 oxygen atoms in oxygen O2. For convenience, we can think of this process as two separate steps. One involving the loss of 4 electrons by the 2 magnesium atoms, and the other being the gain of 4 electrons by an oxygen molecule. This process. Each of these steps is called half reaction, which explicitly shows the electron involved in redox reaction. The sum of the half reaction gives the overall reaction, this one. Or if we cancel the electrons that appear on both sides of the equation, we can write the short form of this ionic reaction. These ones. The term oxidation reaction refers to the half reaction that involves loss of electrons. Chemists originally used oxidation to denote the combination of elements with oxygen. However, it now has a broad meaning that includes reactions not involving oxygen. A reduction reaction is a half reaction that involves gain of electrons. In the formation of magnesium oxide, magnesium is oxidized. It's said to act as a reducing agent because it donates electrons to oxygen and causes electron to be reduced. Oxygen is reduced and acts as an oxidizing agent because it accepts electrons from magnesium, causing magnesium to be oxidized. Note that the extent of oxidation in redox reaction must be equal to the extent of reduction. That is, the number of electrons lost by reducing agent must be equal to the number of electrons gained by an oxidizing agent. The occurrence of electron transfer is more apparent in some redox reactions than ours. metallic zinc is added to a solution containing copper sulfate, that zinc reduces copper 2 plus by donating 2 electrons to it. And you can see it in this reaction. In the process, the solution loses the blue color that characterizes the presence of hydrated copper 2 plus ions. You can see this one is before, is at the start of reaction, and then at the finish of reaction. So this solution lost its blue color. In this slide, you can see the half reactions. And similarly, metallic copper reduces silver ions in a solution of silver nitrate, like in these reactions. And in this slide, you can see the result. And color become blue. The definitions of oxidation and reduction in terms of loss and gain of electrons apply to the formation of ionic compounds such as magnesium oxide and the reduction of copper ions by zinc. However, the definition don't accurately characterize the formation of hydrogen chloride and sulfur oxide, because HCl, hydrogen chloride, and sulfur dioxide are not ionic but molecular compounds. No electrons are actually transferred in the formation of these compounds, as they are in the case of magnesium oxide. Nevertheless, chemists find it convenient to treat these compounds as redox reactions because experimental measurements show that there is a partial transfer of electrons, for example, from hydrogen to chlorine and from sulfur to oxygen. To keep track of electrons in redox reactions, it's useful to assign oxidation numbers to the reactants and products. An atom's oxidation number, also called oxidation state, signifies the number of charges an atom would have in a molecule or an ionic compound if electrons were transferred completely. For example, we can rewrite the previous equation with these equations for the formation of hydrogen chloride and sulfur dioxide by using this reaction. There's small changes here, and the numbers above the element symbols are the oxidation numbers. In both of the reactions shown, there is no change on the atoms in the reactant molecules. Thus, their oxidation number is 0. These ones. For product molecules, however, it is assumed that a complete electron transfer has taken place and that atoms have gained or lost electrons. The oxidation numbers reflect the number of electrons transferred. Oxidation numbers enable us to identify elements that are oxidized and reduced at a glance. The elements that show an increase in oxidation number, for example, hydrogen and sulfur, in the present in these examples, are oxidized, chlorine and oxygen are reduced, so their oxidation numbers show a decrease from their initial values. Note that the sum of the oxidation numbers of hydrogen and chlorine in hydrogen chloride is 0, plus 1 and minus 1. Sum of these numbers is 0. Likewise, if we add the charges of sulfur and 2 atoms of oxygen, the total is 0. The reason is that the hydrogen chloride and sulfur dioxide molecules are neutral, so the charges must cancel. Among the most common oxidation-reduction reactions are combination, decomposition, combustion, and displacement reactions. A more involved type is called dispersation reactions, which will also be we will discuss there. Okay, let's start from combination reactions. Combination reaction is a reaction in which 2 or more substances combine to form a single product. For example, formation of sulfur dioxide from sulfur and oxygen, and aluminium bromide from aluminium and bromine. In this slide you can see this reaction. For example, this is a burning of sulfur in air. This is a reaction of aluminium with bromine, and this is a burning of sodium in chlorine. The next type is decomposition reactions. These reactions are opposite to combination reactions. Specifically, a decomposition reaction is the breakdown of the compound into 2 or more components. For example, reaction decomposition of hydrogen oxide, decomposition of potassium chloride and sodium hydride. In these pictures you can see these reactions. For example, the reaction of heating of mercury oxide that decomposed to mercury and oxygen, and heating of potassium chloride that also produces oxygen. A combustion reaction is a reaction in which a substance reacts with oxygen, usually with the release of heat and light to produce a flame. The reactions between magnesium and sulfur with oxygen that we described earlier, also combustion reactions. Another example is the burning of propane, a component of natural gas that's used for domestic heating and cooking. This one. Assigning an oxygen number to carbon atoms in organic compounds is more involved. Here we focus only on the oxidation number of oxygen atoms, which changes from 0 to -2. In displacement reaction, an ion or atom in a compound is replaced by an ion or atom of another element. All alkali metals and some alkaline F metals, which are the most reactive of the metallic elements, will displace hydrogen from cold water. For example, in this reaction you can see sodium reactive water. Product will be hydrogen and sodium hydroxide, and particularly the same reactions with water with calcium. Many metals, including those that don't react with water, are capable of displacing hydrogen from acids. For example, zinc and magnesium don't react with cold water, but react with hydrochloric acid, for example, like in these reactions. A metal in a compound can be displaced by another metal in the elemental state. An easy way to predict whether a metal or hydrogen displacement reaction will actually occur is to refer to an activity series. Sometimes it's called electrochemical series. Basically, an activity series is a convenient summary of the results of many possible displacement reactions, similar to the ones already discussed. According to this series, any metal above hydrogen will displace it from water or from an acid. But metals below hydrogen will not react with either water or an acid. In fact, any metal listed in this series will react with any metal in a compound below it. For example, zinc is above copper. So zinc metal will displace copper ions from copper sulfate, for example, or another salt. Zinc is here, copper is here, so zinc will displace copper ion. And dispersation reaction, a special type of redox reaction is the dispersation reaction. In a dispersation reaction, an element in one oxidation state is simultaneously oxidized and reduced. One reactant in a dispersation reaction always contains an element that can have at least 3 oxidation states. The element itself is in an intermediate oxidation state. That is, both higher and lower oxidation states exist for that element in the products. The dispersation of hydrogen peroxide is an example of a dispersation reaction. For example, here the oxidation number of oxygen in the hydrogen peroxide is -1. And it's increased to 0 in oxygen and decreased to -2 in water. Another example is the reaction between molecular chlorine and the sodium hydroxide solution, or potassium hydroxide, or another strong base. This reaction describes the formation of household bleaching agents. For it is the hypochlorite ion, this one, that oxidizes the color bleaching substances in stains, converting them to colorless compounds. And chlorine has the charge +1. And also chloride ion has a charge -1. So it's also an example of dispersation reaction. Finally, it's interesting to compare redox reactions and acid-base reactions. They're analogous in that acid-base reactions involve the transfer of protons, while redox reactions involve the transfer of electrons. However, while acid-base reactions are quite easy to recognize, because they always involve an acid and a base, there is no simple procedure for identifying a redox process. The only sure way is to compare the oxidation numbers of all the elements in the reactants and products. Any change in oxidation number guarantees that the reaction is redox in nature.